Hello again. In this video, I'm going to go over this homework problem from 5.3. And in this problem, we're supposed to simplify the following expression. And the expression is we're taking the derivative of this definite integral with respect to x. Okay, we want to try to simplify this expression. Okay, so let me show you how we can simplify it. Okay, in order to simplify this expression, we're going to appeal to the first part of the fundamental theorem of calculus, which says that if f of t is continuous on a closed interval from a to b, then the derivative with respect to x of the definite integral of f from a to x is equal to f evaluated at x. Okay, so if you take the derivative of this definite integral, you get f of x, but only on the closed interval from a to b. Okay, so let's talk about this. Suppose you have a function, and I'm going to call this the t-axis here. Suppose you have a function that's continuous from a to b. Okay, and now suppose you actually you start at a and you stop at some point x in between a and b, and you want to find the net area trapped between f and the t-axis. Okay, how would we describe this area in here? Well, we can describe the net area trapped in here between f and the t-axis from a to x. We can describe that with a definite integral. It's simply the definite integral from a to x of f of t. Remember, this gives you the net area trapped between f and the t-axis starting at a and ending at x. Now that describes this net area here. Okay, in fact, sometimes we call this the net area function. And notice, so I'm going to call it capital A for net area. And notice that it is actually a function of this x value. If this x value were over here, the net area in here would be larger. If it were over here, it would be a little smaller. So this net area function is actually a function of x. And so the fundamental theorem of calculus tells us what happens when we take the derivative of this net area function with respect to x. If you were to take the derivative of this net area function with respect to x, you would simply get f, not evaluated at t, but f evaluated at this upper limit. So f evaluated at x. Okay, and of course that would be, you could also write this as just a prime of x, right? That's the derivative of the net area function. Okay, and so those are equal, but only on the closed interval from a to b, where f is continuous, right? The interval that f is continuous on, these two are equal on. Okay, so let's apply this, the first part of the fundamental theorem of calculus to this expression and try to simplify it using the fundamental theorem of calculus. Okay, so what we're going to do is we're going to take this definite integral, just this part right here, the definite integral here, and we're going to call that y, just to give it a name. And then I'm going to write this as 1 over t squared plus 20 times dt. That's the same thing as what's written here. When you multiply these two together, you get dt times 1, which is just dt. And of course, 1 times t squared plus 20 is t squared plus 20. So you can write it either way. I prefer to have it written this way, and that way we know our f of t. F of t is 1 over t squared plus 20. Okay, but again, I'm calling this definite integral, I'm calling it y just to give it a name. Okay, so if we do that, then we're really just finding dy dx. We're taking the derivative of this, which I'm calling y, with respect to x. Okay, that's what this is. Okay, so we're going to try to figure out what dy dx is. Okay, I'm also going to call this upper piece, this upper limit up here, I'm going to call it u because I just want it to be one variable. I don't want it to be squared or cubed or anything like that. So let's call x squared u. Okay, if I do that, then this is simply the definite integral from 0 to u of 1 over t squared plus 20. Okay, and now we're going to try to find dy dx. We're actually going to find dy dx using the chain rule. Now, if you remember, the chain rule says that dy dx is the derivative of is equal to the derivative of y with respect to u times the derivative of u with respect to x, where y is a function of u and u is a function of x. And notice we do have that here. U is a function of x, and our y is equal to this. That's actually a function of x. It depends on this up here. I'm sorry, it's actually a function of u, right? The way we've written it here. Okay, this is actually an area function, right? This right here is an area function, and it's a function of u. Okay? So y really depends on u. Okay, so let's find it so we're going to find dy dx using the chain rule. All right, so let's start with dy du. Okay, well, this is y, right? So you're taking the derivative of that, right? Remember, y is equal to this, right? This definite integral. So you're taking the derivative of this definite integral with respect to u. Well, what is that? Okay, well, this is an area function, right? This gives you the net area trapped between this function and the t-axis, starting at 0 and ending at u, right? So that's a net area function. And notice I'm taking the derivative of it with respect to u, which is the upper limit here. And so you can see by the fundamental theorem of calculus, part 1, that this derivative over here is going to be f evaluated at u. Where f of t is 1 over t squared plus 20. Okay, and so if I evaluate this function at u, I'm going to get 1 over u squared plus 20. Okay, so that's my dy du. All right, now we just need du dx. Okay, but the derivative of u with respect to x would just be the derivative of x squared with respect to x, and that's just 2x. Okay, so then let's just go back and fill this in. dy du is 1 over u squared plus 20 times du dx, which is 2x. And then I want to replace this u. U is actually equal to x squared. So just to finish this off, first of all, I get 2x on top. And then u squared plus 20, but u is x squared. And so that's really x to the fourth power. And so you're left with 2x over x to the fourth plus 20. All right, so that's my dy dx, right, using the chain rule. And so back up here, we've solved for dy dx. It's 2x over x to the fourth plus 20. And that is the, that dy dx is the derivative of this definite integral with respect to x, which is the function that the expression that we're trying to simplify. Okay, so let's just double check it. So you can see, yes, it's 2x over x to the fourth plus 20. Okay, so I hope you found this video helpful. I'll continue to work on some of the homework problems from Chapter 5, and hopefully you'll get a chance to look at some of those videos as well. Thank you for watching. Bye-bye.